Good morning, everybody. So I would like to present here the view from the lab and the point of the lab from the vitamin D testing. And of course, in labs, you know, we are working with reference range. You know how we make reference range in a lab. That's not very clever. We are not very clever people in labs. You know, if you want to establish good reference range, you take a population of young, healthy people, just like you all, ladies and gentlemen. You measure the assay, the measurement, and you make the mean. You take standard deviation on 120 patients or healthy subjects, and you establish your reference range as being the mean. Here you've got the mean or the median, minus 2 sigma, plus 3 sigma, and this is your reference range. If your distribution is not Gaussian, we make some tricky statistical things to make it Gaussian, and that's really how we do to establish our reference range in the laboratory. But look at what Bob Hinney told us in 2000. He said that if you want to correctly interpret 25-hydroxy level in the patient, forget what the labs put as reference range. We were not very pleased to see that, but he was absolutely right. And what Paul Lipp said, that if you want to have a good interpretation of your vitamin D results, you have to use health-based reference range instead of population-based reference range. Good. But how can we make the difference between the normal and the deficiency in vitamin D? This is a good question, and still not really well answered. But perhaps we've got some tricks to have follow different points. Perhaps that the health-based reference range, as Professor Shab mentioned, could be the relation between PTH and 25-hydroxy vitamin D values. Already shown that, we showed that the same slide, more or less. Everybody's showing this slide. But perhaps it could be the good way to make reference range. As he also mentioned, Professor, we could also have the range, the relation between 25-hydroxy D and the fractional calcium absorption. This is also perhaps another thing to follow. Perhaps that we, and this is for me something that's very interesting, that we have as the reference range, the 25-hydroxy vitamin D levels that were obtained in positive randomized controlled trials, which really demonstrate an effect of vitamin D. This is something that could be very interesting. What was the level that was reached in these studies? Could be also the 25-hydroxy levels observed in patients suffering from osteomalacia. This is also something that we could use. And perhaps finally, could be the 25-hydroxy levels that our ancestors had. We're making some paleontology, but what was the level of this ancestor? What is the native, natural vitamin D level of the human? Well, perhaps that we try to answer this different question. As already mentioned previously, this is the relation between PTH and 25-hydroxy-D, and it's true that there is an inflection point, but what is the real value between 20 and 30 here? That's not, you know, in all these points, that's not it's very clever to put here, that this is really the inflection point. When, of course, you've got patients that got values of 25-hydroxy-D above 30, but which have a secondary hyperpara, or patients with very low value of vitamin D, which has normal PTH. So perhaps that we need something that we should tune better our reference range for vitamin D. Absorption of calcium from diet, as Professor Shab mentioned, if you increase your vitamin D, there will be an increase of your absorption from calcium from your gut. This is true, and this cutoff is here for 32 nanogram, 80 nanomoles. This is a very nice study published by Bob Hinney, but done in one patient. So perhaps that it's true, but is it sufficient to say, okay, this is 30 or this is 20? In interventional studies, what are the levels that we observed in positive randomized controlled trial? Yeah, there are now more and more studies coming on the market showing benefits of vitamin D treatment in diminution of fracture risk, diminution of falls, as mentioned, cancer, teeth loss, blood pressure. But all these studies, interventional studies, when you give vitamin D or placebo, you have to have a level of 30 nanogram per ml to have a positive effect of vitamin D. If you do not have this level, you do not have positive effect of vitamin D. And this is what happened in the WHI study where they gave 400 units and never reached 30 nanogram per ml. Very interesting study in Germany. Here, these were German drivers who died after a car accident and car crash. So they made a bone biopsy and then determined the vitamin D and to see if there were malacia or not. And this was published in 2010. And here is the osteoid volume compared to the bone volume. If you are above 2% of osteoids, you are considered as suffering from osteomalacia. And here, what they show is that 6 on 29 patients that died from accident care, they were healthy people, 6 out of 29 with value ranging from 20 to 30 presented signs of osteomalacia, whereas if you were above 30 nanogram per ml, you had no sign of osteomalacia. This is very interesting, but again, can we compare the blood obtained from a dead individual? It's not really the same matrix. So this could be also a little bit to interpret, and there are papers that say, okay, is it really correct to interpret things like this? But at least this is very interesting. Finally, of course, we never have the values of our ancestors. That's not possible, unfortunately. But there are people living in Africa, in the middle of Africa, in very high level of altitude that really have a more ancestral way of life, which do not cover themselves too much, which are farmers or hunters, and are just living with a natural way. And a Dutch team managed to have the values here in the Maasai population and in the Hadzabe population. And the mean 25-hydroxy-D observed in this patient, well, this not patient, but in this population were 47 nanogram per ml in the Maasai and 43 in the Hadzabe, showing that if you expose naturally yourself with a dark skin, just like our ancestor had, you will have something that range from 20 to 66 or 58 to 64. So it could be very interesting also to say that this is probably, perhaps, the values that our ancestor had before pollution and things like this. But actually, there is no consensus on what is the threshold for vitamin D. The Institute of Medicine in IOM published in 2011 that a 25-hydroxy serum level of 20 nanogram is largely sufficient and covers 97.5% of the whole population. So for them, the threshold should be 20 nanogram per ml. As Professor Shab mentioned, the Endocrine Society and my colleague also say that vitamin D deficiency is considered as 25-hydroxy below 20, and the insufficiency between 20 and 30. There is still, up to now, no consensus. And what is very funny is that when you go to the conference where those experts from the IOM of the Endocrine Society are together talking on vitamin D, they show you exactly the same slides, telling, hey, look, it's 20, and the others say, look, it's 30. It's, even if the experts do not agree, can we agree on what is this reference range? But I think that they could agree together because the IOM does not focus patients. The IOM focuses normal population, not unhealthy population. Whereas the Endocrine Society focus not healthy population. They are focusing on patients and not the IOM. And also, if we come with the view from the lab, we say that all of these values, 20, 30, have been obtained with one kit, with the diacerin radioimmunoassay. And now, as already mentioned, there are lots and lots of kits coming on the market. So can we transpose these 20 or 30 nanogram to all the kits of vitamin D? This is another question. So what could we recommend for the vitamin D testing, at least from the lab science point of view? First, do not screen the population. As you mentioned, in my country, it's also some kind of fashion. Everybody wants to know his vitamin D levels. It's no sense. There is not a blood sampling request without a vitamin D determination by now. It's amazing. So it's too much. So there is not a screening. It's a monitoring. You should use the 25-hydroxy vitamin D determination as a monitoring of a therapy. When you give vitamin D to the patient, you should monitor. And this is completely different. So in which patient should we monitor? Because we know that if we do not reach a certain level, we are not efficient with our treatment. And in this patient, CKD patient, osteoporotic patient, hyper and hypoparathyroid patient obese, so having a bypass, lots of patients are very, very deficient in vitamin D with a bypass. HIV, as already mentioned, cancer and things like this. We should target 30 nanogram per ml. Whatever the way you are at 30, but you have to target 30, and you have to control that your patient is at 30 nanogram per ml. So we are really talking about a monitoring. You give the treatment, you monitor the answer. And you should, because of the compliance, you should control frequently or at least annually or each 18 months the 25-hydroxy levels. So let's move to the determination. And the pre-analytical phase, vitamin D is something that is very stable in your blood. So when you take a blood sampling from a patient, you can leave it just like that for many hours. There is no degradation of vitamin D. It's very, very stable. And you can just leave it at room temperature for many years, for many days, and there will no decrease in the 25-hydroxy levels. You can well, from the blood collection tubes, some assay, and this you should be cautioned on that, cannot be run on plasma, but the serum is the best metrics to run the vitamin D. Watch out if you are running tandem mass spec method, because in some gels you can have some interference which could raise the 25-hydroxy vitamin D. So this is something that should be taken into consideration. Let's move to the analytical phase. So it's more 42 years ago we had the first kit for, no, it was not a kit, but the first determination of vitamin D, which was with vitamin D binding protein was the ligand. They was using tritiated 25-hydroxy as the tracer. So it was a very, very complicated technique. In the late 70s, the first HPLC methods were available. In 1985, the first radioimmunoassay with iodine 125 as a tracer. And it's still more or less the same techniques with all the chemiluminescent or ELISA methods. And since 2004, we've got tandem mass spec method to run vitamin D. Very, very complicated to determine vitamin D because it's a very, very light profile molecule. So this is one of the most complicated molecule to run. You have to displace the vitamin D from the vitamin D binding protein, and you assume that it's 100% this displacement, but you're never sure that it's 100%. You got lots of difficulties to prepare the standards. You cannot just add vitamin D to a serum to make a standardization because you've got matrix effects. So it's very difficult to have a good standardization. It circulates as D2 and D3, 25C-D2, 25C-D3, and of course you need to recognize both forms. This is very important. If you are running just in non-equilibrium states, you don't have a good equilibrium between the antibody and the vitamin D. So it's quite complicated to have good results when you are not at the equilibrium. You've got different interference with the epimer, the C3 epimer, which is present in young children, or the 24-25 vitamin D, dihydroxy vitamin D, which is produced when you give higher dose of vitamin D. So this can be good. This can give interference with immunoassays. You've got matrix effects with a uremic sample from hemodialyzed patient. You've got matrix effects with the vitamin D binding protein in pregnant women. So it's very, very complicated to have a good vitamin D determination. So what is on the market actually? So it's in 2012. More or less, you've got 125 labs using. This is the DQuest, which is an external control, which is run by 1,000 labs in the world. And what are those methods? Well, most of them are immunoassays. I would say that 90% of the methods that are on the market now are immunoassays, with the most prevalent being the liaison and the IDS-EIA or ISYS. And there are 125 labs that are running tandem mass spec method. You've got less than 50 labs still running radioimmunoassay in 2012. So what are the results of those QC? These are the last ones, the controls of October 2012. What we can see here is that this assay, which is, this is the coefficient of variation between the labs. Here, this is the Siemens Centaur assay, which presents a tremendous coefficient of variation of more than 20%, much more important than all the other methods. So this assay has got a real problem, and in my opinion, should understand how it's still on the market. When you look at all the others, ISYS, tandem mass spec, liaison, Roche, Abbott, they've got more or less the same CV. What it shows is that even if you are running a tandem mass spec method, you don't have a better CV than if you are running an immunoassay. So that's forced to think that if you got a tandem mass spec, you've got a reference method. That's not true. You will have the same CV. So let's look now at the mean that was obtained on these controls. Well, you see that there are basically two different calibrations. Here are the results obtained with the tandem mass spec. Here, tandem mass spec, CMS, MS, the gray here. And look here, this is the ISYS, and this is all the others. So all the kits, most of the kits, sorry, are calibrated again the RAA from diacerin because it was the first method that was on the market. And you've come now with the tandem mass spec showing that the standards that were in the radioimmunoassay from diacerin were lower than expected. So if you are running a tandem mass spec, you will have higher values than if you are using the radioimmunoassay or a kit that is calibrated against this radioimmunoassay. So this is quite complicated, but if there is now a real need to standardize these methods, because you don't have the same value if you are running a method that is calibrated against tandem aspect, or if you are running a method which is calibrated against the radioimmunoassay from DiaSorin. So there are lots of, well, now 2 papers that have shown that now there is an accepted reference method that is run by one reference lab in Ghent in Belgium. And this is the reference method, which does not mean that if you are running the same, well, the tandem aspect, you've got the reference method. So this reference method have allowed to standardize the measurement of 25-hydroxyvitamin D. And how does it work, this standardization? Here you've got a sample of 80 patients with value ranging from 10 nanograms to 80 nanograms, or to 22 nanomoles to 200 nanomoles. And these samples have been determined with the reference method in the University of Ghent. And you've got here the exact value, well, if maybe you can be exact, but the exact value of this, one of each samples. This panel has been sent to the users that want to recalibrate their tandem aspect against this reference method. And then it will come to immunoassay producers that will standardize their assays according to this kind of panels. So this problem can be resolved. So there will be less problems in standardization of vitamin D. But perhaps that there will be unresolved problems, and perhaps there will be new problems. When you look at the vitamin D2 here, it is here, you've got absolutely no D2 in those samples. So if so there will be a standardization of D3, but not of vitamin D2. This is something that should be resolved, but this problem of D2 will not be resolved. There are lots of users do not separate, when they are running tandem aspect, they do not separate the C3 epimer. So this remains a problem, because you consider that this C3, which is probably not active, is considered by tandem aspect users as vitamin D, 25-hydroxyvitamin D. So that's a problem. And again, this will not solve the problem of the matrix of linked to the vitamin D binding protein. Pregnant women have much higher vitamin D binding protein than non-pregnant women. Hemodialyzed patients, due to acidic media, due to the uremic media, they do not behave in the same way as the others. So these problems will not be solved by this standardization, and there will be still some work that will have to be done on that. And finally, we've been talking about cutoff, 20 nanograms, 30 nanograms, even 40 nanograms. If we re-standardize, we will need to have new cutoffs. So instead of talking about 20 nanograms or 30 nanograms, we will be talking about 20 will become more or less 30, 30 will become more or less 40, and 40 will become more or less 50. So the physician, so it's been a long time just to get used to this 20, 30, whatsoever nanogram cutoffs. We will come with new cutoffs if we re-standardize our assays. So it's something that we have to take that into consideration. And that was my last slide, and I thank you for your attention. And of course, if you have questions.
I will try to give a short overview over the use of bone turnover markers in the clinical situation, and it is still also, as Professor Saab mentioned, with vitamin D measurements, sometimes a controversial issue how to use these markers, and you may find doctors that are still very critical of these markers. I've been using them now for a total of 5 years and in the clinic, and before I worked in the pharmaceutical industry, I have extensive experience with using them in a trial environment to monitor the effects of osteotropic drugs. My experience personally is that they are very applicable and very useful in my clinical handling of patients, and I'll give you some examples of that. I'm fully aware of the fact that in most countries still the measurements are not reimbursed. They are reimbursed in my country, so I have an easy access, and that's of course something that has to be taken into account when implementing these markers. What I'm going to deal with in my overview is how they relate to bone remodeling, what's the validation, the objections that we are encountering when we talk about bone markers, and also especially the variability that has been considered very high. What I want to submit to you is that that's not the case anymore with the new serum-based markers. And finally, give some examples on how you could use them in clinical decision making, and more importantly, where I think they have their biggest role is in the monitoring of your therapies, where I find that these markers actually provide more information than BMD testing. These are the markers that I'm going to deal with. Here you have a remodeling sequence with bone resorption followed by bone formation, replacing old bone with new bone. And you have markers that reflect the resorptive capacity of osteoclasts. Previously we measured urine pyridinium crosslinks. Now everything is serum-based, either serum CTX or NTX, and internationally the focus is on CTX as being the more dynamic and more reproducible marker. And then you have the tartrate-resistant acid phosphatase that, in my experience, in specific conditions can be of value, but otherwise it's not very informative. The main marker to use to monitor bone resorption is CTX. Formation markers, you have a whole row also, osteocalcin, that has been on the market for a long time. It's a useful marker, but it has some issues because it has response elements in the gene that are responsive to vitamin D and corticosteroids. And therefore you may get perturbed values when people are treated with corticosteroids or if they are vitamin D deficient. We have shown that in a previous study. The most useful markers, again, are serum-based collagen markers like CTX, which is also a collagen marker. And here, again, the focus internationally is on P1NP. Actually, bone-specific alkaline phosphatase is a very robust marker also, and I use it extensively. But in terms, if you had to choose one marker out of all these, it would probably be P1NP. It's the most stable marker. It can also reside on the table, kitchen table, for a week without changing, and has a very low variability. It doesn't have as high a diurnal variation as, for example, CTX. CTX, you also have to remember that patients should not eat before they get the value, and they should be taken between 8 and 10 in the morning because it has quite a significant diurnal variation. So the collagen markers that are being subject to standardization internationally now is the type 1 collagen markers that reflect bone turnover at the matrix level. And the P1NP is a propeptide. It is a fragment of collagen that is split off the collagen molecule when it is deposited in bone matrix and aggregates in bone matrix. So it's kind of stoichiometrically reflects the amount of collagen that is being laid down into the bone matrix. And the CTX is also based on collagen, but it's based on the fact that once collagen is deposited in the bone matrix, it'll take a long time before it's being resorbed usually, and lying there, it will create spontaneously these collagen crosslinks that link the collagen molecules together. And this telopeptide part here, CTX, the C-terminal telopeptide part, you can distinguish between newly formed collagen and old collagen because of the presence of these crosslinks. And you have various peptides that fragments that contain this crosslink, and then you can measure in your assay. These are the objections that we frequently encounter when we discuss it internationally. And especially in the US, there's still a lot of skepticism towards bone markers. There are too many markers, yes, but what I told you is that you could concentrate on just one or two, CTX and P1NP. They are too noisy, and they need to be validated. They do not correlate to fracture risk. Clinicians need a clear target, and we will know if they are responding. Just ask about compliance. I think all these issues I'll deal with, and I'll show you that they are not valid objections. Validation. We have bone histomorphometry. That's one of my own studies in the early days with osteocalcin, and also ICGP, that was an older resorption marker, and P1CP that has now been replaced with P1NP, but that was what we had in 1993. And we could show even with these markers a nice correlation to bone resorption as assessed in bone biopsies from the iliac crest, and also bone formation volume-based as assessed in the iliac crest. So these markers reflect bone turnover at the tissue level. We have also done calcium kinetics, because you could say the iliac crest is only a small part of the skeleton. What about the whole skeleton? And there we have a calcium kinetics study when I was at the Mayo Clinic, where we looked at calcium kinetics and BGP, which is osteocalcin. It was before we had standardization of the nomenclature. And here again you see a nice correlation in non-osteoporotic and osteoporotic patients between calcium kinetic accretion rate as a measure of bone formation and serum osteocalcin. So they are pretty well validated, these markers. Variability. And there are many sources of variability. One of the main ones you have to take into account is fracture. If the patient has had a recent fracture, the markers may stay elevated for half a year. That has been shown by Richard Eastle, for example. There are diurnal variations, day-to-day, seasonal variations due to vitamin D changes, for example. Age and sex, diet, as I said, CTX is sensitive to eating, physical activity, alcohol, tobacco, and diseases and drugs. These are factors you have to take into account, especially when you measure the markers in a situation where the patients are not being treated. But I would submit that if the patients are being treated, as I'll show you, with turnover suppression drugs like bisphosphonates, like hormone replacement therapy, then this variation becomes less of an issue because the markers are way down at the lower level of the reference range, so this variation does not really play a role. And that has been my practical experience also. This is the study by Richard Eastle's group, where they looked at the day-to-day variability of P1NP in 21 healthy young women over 10 days. And you see that there isn't much of a variation. There were a few outliers, but generally there isn't much of the variation within the reference range. And actually you end up with coefficients of variation of 7 to 9%, which is absolutely reasonable to use in a clinical setting. This gives you a least significant change, i.e. what does it take to say that the one measurement to the next is significant. It's around 30%, 20% for two. Here again, P1NP comes out very favorable, around 20%. But if you practically, for any marker, say, I will call it significant when it's over 30%, then you're okay. And you can easily get changes of 30% with bone markers. In clinical decision making, you cannot make the diagnosis of osteoporosis based on bone markers. But bone strength, that is the ultimate result and the decrease of which results in osteoporotic fracture, is a mixture of the amount of bone, the distribution of bone mass, bone architecture, and finally bone material properties. Numerous studies have shown that bone turnover affects all three of these. That's probably why bone turnover markers are so informative in the clinical practice. And if you look at the secondary osteoporosis cases, these are the majority of diseases that are known to be associated with secondary osteoporosis. Most of them, like hyperparathyroidism, like hypogonadism, like aromatase inhibitor treatment, like renal insufficiency, they're all thyrotoxicosis, vitamin D deficiency, all associated with a high turnover state. And when you deal with bone diseases, you kind of appreciate that high turnover is not good for the skeleton, because it destabilizes the skeleton and increases your fracture risk. There are numerous data on that. So generally, in most cases, if you do not use anabolic drugs to really build more bone into the skeleton, the primary aim of your treatment in bone diseases is to decrease turnover, because that will stabilize the skeleton and reduce fracture risk. And this is also why these anti-resorptive drugs are so effective in primary osteoporosis, because you have two defects in osteoporosis as shown here in the lower panel. This is normal bone remodeling, digging out a resorption lacuna, average depth of 50 microns, which is completely refilled by osteoblastic bone formation, replacing old bone with new bone. In osteoporosis, you have two defects. You have one of osteoblastic fatigue that leads to incomplete refilling of the hole dug out by the osteoclast, which means that for every remodeling cycle you decrease bone mass. And this is further accentuated in severe osteoporosis in most cases, not all, but most, by a high turnover state that not only leads to accentuation of this deficit, but also generally destabilizes the bone. And Young normal bone develops into osteoporotic bone by losing in cancellous bone cancellous elements and trabeculae. And here again it has been shown that you lose more bone the higher the turnover you have, because then the risk that resorption digs all the way through a trabeculum and leads to trabecular loss is higher. And not only do you lose bone, but you also get these stress risers when you have high turnover. Here you have cortical bone in a high turnover state, and here after, in a low turnover state or after treatment with an anti-resorptive drug. And this really shows you that it's not all these holes in the cortical bone due to Haversian remodeling also leads to the occurrence of these stress risers that are material instabilities in the bone matrix that further increase the risk of fracture. By giving an anti-resorptive drug, by lowering turnover, you stabilize the bone and get much less anti-fracture efficacy, with the result that with the most effective anti-resorptive drugs we have nowadays, the parenterally administered drugs like aclasta, bisphosphonate, or denosumab, monoclonal antibody, you reduce the risk of fracture in the spine by 70% and hip fracture by around 45%. And this just shows you that you can use bone markers to predict bone loss. If a patient is in a high turnover state, it will lose more bone. And it has clinical consequences. I especially use it when I have a patient who is at the borderline of intervention based on BMD T-score, which is minus 2.5. But should I start treatment or not? If the patient has a very high turnover, I would probably start treatment to protect this patient, because I know that the additional component of high turnover will lead to a higher degree of bone loss. Here on the y-axis you have percent change in spine BMD. Here you have NTX in this study, and this is the highest quartile, and you see they have a much higher bone loss rate than the lower NTX levels. So there is a correlation between high turnover and bone loss. And also this from the Offaly study in France, where they showed Pierre Delmas' group that the combination of CTX and BMD gave you a better prediction of fracture than BMD or CTX alone. So I use a combination of BMD measurements and bone markers in my practice, because I think it gives me a better evaluation of the patient than just BMD alone. I also think that you can use it in other cases and where I have found them useful, although this is not based on huge controlled clinical trials. This is my own subjective impression, but also based on some literature data. Bone involvement in metabolic bone disease. For example, primary hyperparathyroidism, you may be in the situation where you cannot decide whether you should operate the patient or not. The calcium is only 2.65. According to guidelines, it should be over 2.75, but do they have other risk factors? And especially in old patients, a lot of these patients actually do not have a high turnover state in their bone. The bone disease of primary hyperparathyroidism is a high turnover bone loss situation. But some patients actually don't have it, and they're the markers, not the BMD. They can have normal BMD, but the markers will show you that the PTH does not really affect the bone. And so if you're after really protecting their bone with your operation, you may not get the result you hope, because they do not have a high turnover state. Thyrotoxicosis also is a high turnover bone disease, and there again, there's a huge discrepancy between the bone involvement in these patients. Aromatase inhibitors and glucocorticoid-induced osteoporosis, same. If you measure BMD and markers in some of the patients, they can take this treatment very well. They do not develop high turnover. And that tells you that you should not be as observant on this patient on glucocorticoids or on aromatase inhibitors unless they have a low BMD. But if they have normal BMD and they have a normal turnover with markers, I'm less concerned about the treatment. I may control them less frequently than patients that are on high turnover. Osteogenesis imperfecta, there are now 2 studies. This is a very difficult diagnosis to make. Clinically, it's easy in some patients, but as you know, some patients may not have the hallmarks of blue sclerae and the other deficiencies of osteogenesis imperfecta in the skeleton. And there are 2 studies showing that the collagen markers, in some cases, and a large proportion of cases of OI, are suppressed. Not surprising, they have defective collagen, so the markers will show it. And if you compare them to other markers like alkaline phosphatase, bone-specific, then you may get some fractions that give you quite good diagnostic power. And finally, stress fractures that are clinically very big problem. It seems, and I don't have large data on that but my own impression is that a lot of stress fracture patients have high turnover, again destabilizing the skeleton, and there you may get some help from measuring bone markers. Now, the most important aspect for these markers, I think, is the monitoring of anti-resorptive therapy and anabolic therapy. In both cases, actually, these markers provide you more information than BMD measurements. What you're after is, of course, two different situations. With anti-resorptive drugs like alendronate, you're after a reduction in markers that ranges between 50 and 70 to up to 90% with denosumab. With anabolic therapy, you are after the opposite. You want to see an increase, and there's only one marker you want to use there. That's P1NP, which has shown the best dynamic changes after PTH therapy. I'll come back to that later. It's very useful because if you use BMD early on during anabolic therapy, you underestimate the effect of your drug. Some of the patients in clinical trials that responded the best to PTH actually showed no change in BMD for the first year. Why? Because they had so pronounced stimulation of osteoblastic collagen synthesis that they produced a lot of collagen, but it was not mineralized yet. And that's why the BMD DEXA measurement did not pick up the change in bone mass, because the collagen was not mineralized yet. When you wait later, then you see the effect of the BMD. But to measure BMD early on during PTH treatment is not worthwhile. The P1NP after 3 to 6 months will show you exactly what you are after, that you get a stimulation of the P1NP. These are changes with anti-resorptive drugs, going back to anti-resorptive monitoring, where you see the changes in histomorphometric evaluation of turnover and the biochemical markers. Generally, the histomorphometric evaluation in cancellous bone is somewhat higher than if you take the whole skeleton where cortical bone is involved also. But they follow each other nicely, and you get some fluctuation with the parenteral drugs like sol and denosumab. You see that denosumab have the highest suppression, over 90% of bone remodeling. Is that dangerous for bone? We have no evidence that it has adverse effects on bone fragility so far. You also have to remember that if you give a bisphosphonate orally, it takes up to 3 to 6 months before you have the maximal suppression of your marker, while if you give it parenterally like zoledronic acid, you get it within a week. So you can change your blood testing there, but I usually test my patients at 3 months, where both treatment regimens will lead to a change in markers and significant reduction. There has been a lot of could you use markers to look at response rates? And when we had the oral drugs like alendronate, there was a lot of disappointment when using markers because there was huge variability. But that's of course because these drugs have a huge variation in compliance. Some patients don't take the drug, and no wonder your drug will not show a response. However, if you use a parenteral drug like zoledronic acid, you get response rates at different time points that hover around 80–90%. Actually, when you measure it early, where you have the best response in markers, because with parenteral drugs you get a certain reduction in response over time, then 97% of patients will show a response with biochemical markers. And also in a study here from Richard Eastwood groups, lasofoxifene, which is a serum selective estrogen receptor modulator developed by Pfizer, which will not make the market due to some safety issues, as far as I know. But again, the response rate, which is not as pronounced as with bisphosphonates, you got a nice coherent response rate, only a few outliers of patients when you measure CTX or P1NP, which are the two best markers we have available. Is there a clear target for clinicians? Yes, I think there is. We know from 2 studies now that you want good suppression of bone markers in the range of 60 to 70%. And this is, for example, highlighted here in the study with alendronate, where they looked at bone-specific alkaline phosphatase and the relation between hip fracture risk or vertebral fracture risk and changes in bone alkaline phosphatase. And you see the more reduction you had in the marker, the more reduction of fracture you had. So the reduction in marker reflects your anti-fracture efficacy. And remember, this is a logarithmic scale, so it's much more pronounced that than immediately meets the eye. Also, they tried to look at what happened to patients that showed less of a suppression versus patients that showed higher suppression. And the cutoff for bone-specific alkaline phosphatase was 30% in this study. And you see, in terms of spine fractures, it doesn't matter. There you got significant reduction in either group. Spine fractures react very favorably to turnover suppression. But if you want to have effect on non-vertebral fractures, hip and non-spine, then you see that the patients who had less of a suppression did not reach a significant reduction in fractures. So you need your markers to tell you whether you have reached your target. And you want your patients to end up at the lower level of the normal range of premenopausal women for all markers. This is newer data with a cluster, zoledronic acid, where actually it was shown that the markers explained 58% of the probability of vertebral fracture versus BMD only explained 40%. And again, there was a curvilinear relationship between the reduction in markers and the risk of fracture of the vertebrae here. And there was much more dynamism, as you see, in the marker response than seen in the BMD response. And in this study, actually, it was shown that you could after 1 year of marker changes, you had a better prediction of anti-fracture efficacy than if you waited 3 years to measure your BMD. So the markers give you a quicker response than BMD. On average, when patients stop to take, for example, alendronate, you see a response with an increase in markers over the suppressed level within a year, while BMD takes usually 2 years before you can see a response there. So they are more dynamic. And these are my own markers, again coming back to variability. Here I have a patient who has been measured since 2005 with osteocalcin on alendronate. Here's the normal range of osteocalcin. This is where I want her to be. These are 3 patients, not much of a variation, very small changes, because in the suppressed state, the variability doesn't really mean a thing. Here you have CTX, where this patient is being treated and ends up here. 2 other patients are just below the normal range, which I like. This is good anti-fracture efficacy from the studies I showed you. Again, not much of a variation in these 2 patients that were on treatment through the whole period. And here you have bone-specific alkaline phosphatase, 1 patient over 6 years, not much of a variation. And here you have 4 patients, 1 being treated here. Again, this is one that got tired of alendronate tablets. Again, a nice variation. So you can use these markers also to see with oral drugs that your patients are taking them, and they're excellent in showing you that. If a patient who has shown nice suppression over many years suddenly starts to show an increase in markers, you know that something is wrong. It could also be that you have to do a new workup because the patient is developing other causes of secondary osteoporosis. Anabolic therapy, again, this is the effect of PTH on bone. You build more bone, on average 30% more bone into the skeleton with PTH over a 2-year period. And here again, if you compare the various markers, just look at the yellow bars, that's the effect on PTH. P1NP comes out as the most dynamic, the best marker to use, and that has been shown in numerous studies, also with newer anabolic regimens. And there's a relation between the BMD response and P1NP changes. So if you measure P1NP after 3 months, which I usually do, then if it's over 10 micrograms per liter, you can tell the patient you get a nice BMD response. We also have data from histomorphometry showing that the early changes in bone markers actually reflect how the bone architecture ends up 2 years down the road. So it's very predictive. And here are my own experiences with P1NP. There's more variability in your response, and the maximum response to PTH is at 6 months here. There's a huge variability, but the least significant change of the drug permits you to say that these are all significant changes. And this is the interesting period, because after that, as we know, the response of the bone cells will decrease to PTH, still building new bone, but not as much as 6 months. So if you want the optimal response to PTH, measure their P1NP at 6 months, and you are able to tell the patient how they will end up. So to conclude, high bone turnover is not good for the skeleton. We need to get it down to stabilize the skeleton, and markers are excellent in showing us how well we perform in that respect with our different treatments. And we have to remember that the bone turnover treatment to all versus IV bisphosphonates is different. you have to wait at least 3 months if you want to monitor all bisphosphonates. But then again, that permits you to do something about the patient's situation. If they don't show a decrease in markers, it's usually bad compliance to the drug. You can discuss it with the patient again and take action. If you had to rely on BMD, you would have to wait a year before you could take action. The variation during reduction of bone turnover is much less, as I showed you. It's not a big deal when you monitor anti-resorptive therapy because bone turnover is down, variation is down. The dynamic range for P1 and P is way beyond the least significant change. Although there's a lot of variability between patients, it's still informative. And so to conclude, I find, and a lot of other colleagues find bone turnover markers useful tools for monitoring both anti-resorptive and anabolic osteoporosis therapies, and in certain clinical situations they will add additional information that permits you to evaluate the patient's situation in a better way. And with that, thank you for your attention.
I'm going to talk about the growth hormone and IGF-1 measurement, and just to give you an overview of the lab on this particular determination, which are not obvious neither. And I will start with the German quality control. So the German Society of Clinical Biology is sending different samples to different labs to test the GH. And here are the results. For instance, it was in 2010, but still the same, actually more or less in the moment. And here are the results that have been observed by a little bit less than 200 labs. For GH, you've got a ratio of 4 from the lower to the higher result. So if these labs are giving a value of 2, these labs are giving a value of 8. So a 4 times manifold difference in the GH measurement according to the lab. IGF-1, a factor 3 between the lower IGF-1 here and the higher IGF-1 here. So there is definitely a problem if you go to different labs, because you will have different results with your GH measurement. But if you go more into details, not into the global situation, but if you go technique by technique, you will see that here all the users of the diastereomere non-liaison, they have all the users will have a value below 3, which can be considered as a cutoff for GH supplementation in GH deficient patients. Whereas Perkin-Elmer users just more or less mitigate it here. Beckman-Coulter, half of the patient will have treatment. Here, half will not have treatment. And with the Siemens, none of the patient will have the treatment. So what it shows that according to the lab, you could give a treatment or not a treatment according to the technique that is used by the lab. This is really a problem. Because we have guidelines. We try to have guidelines with cutoffs because, yes, Eric mentioned clinicians love cutoffs. And if we use the same cutoffs, these results show that these results show that we cannot at all use the same cutoff according to the kit. So if, for instance, just to show you the difference, if you are using cutoff, for instance, here is a oral glucose tolerance test, measured by 2 different assays. And if you are using a cutoff of 1 microgram per ml to see if those acromegaly patients are treated correctly, you will see that all these, among these 2 different instruments, the Delphia here and the Imulite here from Siemens again, you got here the results show that if you are you use the 1 microgram per liter cutoff, 85 of the patients here will be cured. But if you're using specific cutoffs for your technique, these results show that less than 50% of your patients will be cured. So again, the use of a global cutoff or specific cutoff will lead you to different clinical decision. And why are there all these problems with the GH and IGF-1 assays? Because there's been different standard preparation that has been used to calibrate the kits of GH and IGF-1. There has been also different units. Some labs are using units per ml, some labs are using mass units per ml. There are also a very, very large heterogeneity of those hormones because they circulate into different fragments. So the cross-reactivity of the antibodies will be different according to the kit that you are using. There are problems of binding protein because these hormones circulate are linked to a binding protein. There are matters of pre-analytics and matrix interference. There are also a large problem of normal reference range. What is the normal reference range of this kind for these kinds of hormones? Just like we go back to vitamin D. And also, these labs should use QC procedure. There has been a paper published in 2011 that clearly defines a consensus for the GH and IGF-1 measurement. And this paper gives recommendations to labs and also to different manufacturers to try to harmonize the measurement of the GH and IGF-1. Here on the slide that will be blue background, it will be GH, and the green will be IGF-1. So if we look at the standard preparation of GH, so on which standard are the kits calibrated? Well, you see that there are 4 standards from 66 here to the 98 here. 2 have a source from the pituitary, and 2 are recombinant standard. And when you look at the units activity of the enzyme per milligram, it goes from 2 to 3. So the standards do not have the same power, does not have the same units. So that's already a first problem. All these kits, this is a paper published in 2005, but you will see the results now. All these kits here have been calibrated against all the different standards. But if we use one single standard, you reduce dramatically the variation between the kits if you are using a single standard and not using all the 4 standards together. So definitely we should use one single standard, and this standard is the IS-985774. Sorry. So this standard should be used to calibrate all the kits of GH just to reduce the variation linked to different preparation of international standard. The results should be expressed in mass and not in units. So labs should not respond anymore in units, they should respond in mass and in microgram per liter of this international standard. For IGF-1, there was also a problem of standardization because what we thought that was the gold standard was actually impure. And there were lots of, this is the time aspect with the result of the chromatography of this standard. You see that there are different peaks. And so the IGF-1 standard is not a pure standard, it's an impure. So the result that had been obtained can be also different. So what are the recommendations for the IGF-1? Again, use a same single standard, the 254 WHO, to calibrate all the IGF-1 kits. This is very important. And this standard is more than 97% recombinant IGF-1. So this is the standard that should be used, and accordingly, there should be a reduction in the variation of the different tests. This is the different isoforms that circulate, of GH that circulates in the serum. There is the more abundant is the 22 kilodalton monomer, but there is also the 20. There are different fraction, acidic, non-covalent, dimers, and things like this that circulates in the blood. The problem is that if you are using an antibody, you will recognize with different extent all these different forms, and that will give you different response for this if you use different antibodies in the same patient. So what should we recommend for the GH? All the assay should be specific for the 22 kilodalton GH, which is the most abundant form. So accordingly, this is very important for the manufacturer. Now, of course, as I mentioned, there are cross-reactivities with the different fragments and with the 20 kilodalton fragment. But if there is a cross-reactivity, the manufacturer should specify what is the cross-reactivity of the 20 kilodalton fragment. Binding protein, GH circulates, we're linked to the GHBP. And if you add GHBP to the serum of the patient, you will see that you will have a decrease in the response of GH, showing that this GHBP can interfere with your GH assay. So this is really important to know what is the cross-reactive, the interference by GHBP, and the manufacturer should specify the degree of the interference of the GHBP when they're producing a GH. There is also IGF-1 also circulates linked to IGF-BP, and this IGF-BP gives also an interference in the assay. How does it work? So if the direct IGF-1 assay, of course, we mentioned earlier, in the younger days of Professor Saab, that there was a chromatography, acidic separation, but it's very time-consuming to have this kind of good IGF-1 reference method. So now we try to separate the IGF-1 with an acid extraction, and you separate the IGF-1 from the acidic labilsum unit and the IGF-BP3. And then you measure the IGF-1 directly. But if there is IGF-BP3 that has not been removed, you will have an underestimation of your IGF-1 value because this IGF-1 will be captured by your IGF-BP3. So what are the new techniques to run IGF-1? Well, it's to give an excess of IGF-2. You add IGF-2 to this media, the IGF-2 in excess will bind the IGF-BP3, and then you can have determine your IGF-1, and you have a good measure of your IGF-1. So you have to saturate your IGF-BP, your remaining IGF-BP with IGF-2, and all the assays now use this technique to run IGF-1. So the method of prevention for the interference of the IGF-BP should also be mentioned by the different manufacturers. From the practical point of view, once you take the blood of your sample, you have to be quite fast on the separation between plasma and cells. We recommend to use serum. If you are using plasma, you have to validate this plasma, so it's better to use serum. And of course, the calibrators, the matrix of the calibrators must mimic the properties of the samples and contain, of course, binding proteins. Let's talk about the reference range. And here is the one oral glucose tolerance test, in acromegalic patient measured by 14 assays in different labs with a single cutoff of 2.5. And here, according to these labs, this patient will be cured, whereas this one may be the case here. So indeed, if you use the same cutoff, you will have different clinical response if you are using different assays. So we need GH assay-specific reference range. We cannot use a single reference range or a single cutoff for all the assays. We need specific assays. And this is very important. If you want to have a diagnosis of acromegaly with an OGTT in a treated patient, you should have a CV that is below 20% at 0.05 microgram per liter. So you have to be very sensitive in the low end of your curve. It's very important that a limit of quantification below 20%. Here is the same for the IGF-1. One sample sent to 23 labs. 23 labs report 6 different assays and provide 15 different reference range. Now, again, there are different reference range for the same test according to the lab. And you have a magnitude of 1 to 3 according to the lab or the assay for the same patient. So, of course, this is, again, problematic. If you want to correlate, for instance, 2 different instruments, this is correlation between the liaison and from the Diasoin and the Limulite from Siemens. You see that you've got basically 0.85 slope. So say, okay, we could recalibrate one against each other, but that's not true, because when you look at the upper range and you look at the lower range, you see that you don't have the same behavior. So you cannot recalibrate the kits against one against the other. So this is something that you really need reference range for this IGF-1 kit. So we should have a reference range which are method specific for IGF-1 and which would be based on random selection for background population. And in children, this is also very important. You have to have good reference range in children for IGF-1, and you have narrower age range, and including the terminal stage of puberty to have good reference range in your children. So the recommendation, gender-specific levels for IGF-1 and for the specific from 6 to 18. There are also ethnicity minor confunders, and of course you have to be cautious if you interpret those results in obese patients because you can have an underestimation. Well, this is also a recommendation that all the labs that are running GH and IGF-1 should participate to an external control. This is very important to see how the assay behaves compared to the other. And this is now the three main kits that are on the market for the GH and IGF-1 determination. Let's have a look at how they are standardized. Well, the GH here from ISYS is standardized again, and the diacerin are standardized again, the recommended international standards. But here, look in Siemens, in Europe and the rest of the world, they've got the good standard, but in the US, they remain with another standardization. So if you have Siemens, you've got two different standardization according to the place where you are on Earth. The IGF-1, okay, it's a good standard for diacerin and for ISYS and diacerin. But Siemens, they still have another standard for IGF-1, which is not recommended anymore. Sensitivity of the kit, 0.05 limit of quantification, so the value that is giving you 20% in the lower range is 0.05 for GH, it's correct for ISYS, it's correct for liaison, but Siemens does not provide this limit of quantification. They just say that their analytical sensitivity is 0.01, but doesn't mean anything. It's just the difference between 0 and 0. They make the difference between 0 and 0.01, but they do not provide the limit of the quantification. For the IGF-1, limit of quantification, 9 here on the ISYS, 15 on liaison, 20 on Siemens. Specificity. ISYS is specific for the 22 kilodalton, and there is no cross-reactivity with the recombinant GH, the pegvisament, whereas the diacerin, they are specific for the 20 and the 22 kilodalton, and there is an interference with the pegvisament. And with the Imulite, there is also specific for both 20 and 22, and there is an interference with the pegvisament. Binding protein interference, 0% for GHBP on ISYS, and it's quite very, very low with the IGF-BP. There is no data on the GHBP interference with the diacerin. There is no data provided by manufacturers with Immunite. And normative data, they are very strong, reliable reference range for IGF-1 with the ISYS, or more than 15,000 samples matched by age and gender, which is not the case with the IGF-1 from liaison, where there is very, very low, just 25 by class H, which is very low and not enough. And Siemens have got very good reference range. So the conclusion of the GH and the IGF-1, well, it remains very difficult to have good kits of GH and IGF-1. There has been progress since the workshop recommendation, but definitely there is still some work that remains to be done. The cutoff that I generally use, 3 microgram or 10 micrograms or whatsoever, or 1 microgram, cannot be extrapolated from one method to the other. And the reference range need to be better set up for some method from the diacerin. This could be improved. Thank you for your attention.